let's take a look at statistics part 2. Okay, this is the section from your math curriculum that covers this. It's just in a small section on statistics. Basically, what you're supposed to do is demonstrate an understanding of probability in society. So that's the word we're going to focus on today, this idea of probability, okay? You could provide examples. They're all over the real world, probability. Any of you that have done or consider things in gambling, probability is probably the most important portion of gambling that you need to know about. Given probabilities, talk about limitations, how it can be used to support or oppose a position, etc., like that. So just like general statistics, probabilities are used to help make a point. So sometimes people like politicians and advertisers will use probability within their statistics to try and make a point to you. Sometimes the way they actually figure out the probability is incorrect. So they'll say things to you like, well, you have a 50% chance of getting it right. How they actually figured that 50% out might actually be incorrect. So today we're going to talk about what that means within the realm of statistics and mathematics. Okay, so here's the terms used with probability. Probability itself is the numerical likelihood of some event occurring, okay? Expressed in either a ratio or a fraction or a decimal or a percentage. It represents a value to you. So for example, if I gave you 2 dice and I said, if you're going to roll the dice, what's the odds, what's the probability that they'll both come up a 1? Okay?
Well, it depends on the dice. You can have
Nope.
die.
Nope. I just said this. I said 2 die. Okay? What's the probability of them both coming up a 1? So don't play a guessing game. What I'm going to do is try and show you the way these sort of values are calculated and produced. Okay. So it deals with the result of an experiment. So for example, if I was going to toss a coin in the air 100 times and generate results, how many times did it come up heads? How many times did it come up tails? The outcome is the results of that experiment. So the outcome of the flipping of the coin would be either heads or tails. Okay? The possible outcomes of an experiment are called the sample space. Okay? The event is an outcome within the sample space. So a simple event is just one simple outcome. So let's not get too lost in this terminology. We're talking about an outcome of, say, a flip of a coin. What's the outcome of that event? It's either heads or tails. Okay? So let's say we have one coin being tossed. The possible outcomes are just 2, heads or tails. So the sample space is heads or tails. There's only 2 outcomes. With a die, there could be 6 outcomes. But then they have those sort of weird die. Any of you ever played games that have like those 8-sided dies and stuff? But let's not get too complicated. Let's stay with the simplest version. A coin, 2 possible outcomes. When you flip that coin, you're going to have an event that will register one of those outcomes. If I have 2 coins and I flip both of them, well, they could both come up heads. One could come up heads, one could come up tails, or the other way around, or they could both come up tails. So there's 4 possible ways that 2 coins flipped in the air would have 2 possible, so there's 2 outcomes, okay? So if I'm tossing 2 coins up in the air, okay, the event that the 2 coins would be the same would be the event where it's both heads or both tails. Okay? So these are the kind of things you think about when you're dealing with probabilities. So one way you could look at it is a little diagram. Okay? I'm just going to call it a tree diagram. So I'm going to toss a coin 3 times. So on the first toss, it's going to be either heads or tails. That's easy, right? That's the first toss. But on the second toss, it depends what I got on the first toss. So if I got heads on the first toss, I'm going to get heads on the second. If I got heads, I could get tails. If I got tails, I could get heads, or tails, I could get tails again. Now I toss the coin for the 3rd time. Well, again, it depends what I got on the one before that. So when you look at something like this, it kind of gives you an idea of what the possible outcomes would have been tossing a coin in the air 3 times. So for example, I could have got heads, 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 right? But I also could have got heads, heads, tails. The question is, how many possible outcomes do you see, all the possible outcomes that the way I would come out if I tossed a coin in the air 3 times? It's not about 7. It's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible ways that it could have come out, okay? And that's the way probabilities should be. They shouldn't be like a guess. They should be something that you can actually calculate. Okay, there they are. Those are the different outcomes of the three toss coin toss. Okay, a theoretical probability are the chances determined by calculating results that you can't do under ideal situations, right? For example, rolling a 4-sided die is a 1 in 4 or a 25% chance because there's 1 chance in 4 to roll a 4, okay? And under ideal circumstances, 1 out of every 4 rolls would be a 4, okay? But that's theoretical, okay? Experimental probability is when you actually do a bunch of experiments. So here maybe you'd flip a coin a certain number of times and actually write down the results. And then from those results, calculate probabilities. That would be where you actually perform an experiment, okay? For example, the possibility of winning a game, okay? This could be done, for example, with, say, our school's basketball team, one of our school's basketball teams. You couldn't really do that theoretically. Maybe to do the probability of the team winning, you'd actually look at how many wins they have, right? So you're doing actual experimentation on the team itself. Okay, but from a pure mathematical standpoint, there's actually a formula for calculating probability, okay? And this is the way the formula goes. The probability of something occurring is the total number of possible outcomes underneath the number of favorable outcomes, okay? So this is written often in this format. They'll say the P with brackets and A. This is read as the P of A, okay? The probability of an event A occurring, okay? So let's not overthink this. Let's try something simple like this. So let's say we had the coin toss, okay? So I have a coin, okay, and I'm going to ask, what's the probability of it landing heads, okay? I know you know the answer, but let's see how it works in the formula. So what I'm writing with the formula is the probability of that event, and it's equal to, okay, the total number of outcomes. How many possible outcomes in a coin toss? 2. Okay, so on the bottom I'm going to put 2. And on the top is the number of favorable. Okay, in other words, the one I'm looking for. So I'm looking for the probability of getting heads. The probability of getting heads in a coin toss. Well, there's only one favorable outcome that I get heads. So it's a 1 over 2 probability, which you could actually do the math on, which gives you 0.5 or 50%. And we learned a little bit about that last time. The way you do this is you actually divide it to get that number, and then this number is multiplied by 100 to get the percentage. But that was a really easy one. Let's try one that's a little bit harder. The probability of getting a 6 on a standard die. Or die being the singular for dice. So your standard dice. What's the probability of getting a 6 for rolling it? Well, let's use the formula. What's the total number of possible outcomes? 6. How many favorable outcomes? Just 1. So 1 and a 6. Okay? There we go. You guys are getting this. Let's go a little bit further. What's the probability of drawing hearts from a deck of cards if I just randomly pull a card out? What's the total number? 52. What's the number of favorable outcomes? Right. Anyone not what's that?
26?
Nope.
No, wait, 13.
13 is correct. Why 13? That's how many hearts are in the deck, right? There. Okay. What's the probability of drawing an ace? 4 out of 52. Because there are 4 aces in the deck. That's the number of favorable outcomes. What's the probability of getting the ace of hearts? 1 out of 52, right. So you guys see the way it works. It's not a difficult formula, but you need to understand what these two values represent. They represent the total number of outcomes and the number of favorable outcomes. Okay, now, yes?
For the hearts, couldn't it be like 1/4 because there's hearts, there's spades,
Yeah.
there's clubs?
Well, wait a minute. Reduce that fraction, 13/52.
Yeah, I know. It's just,
It becomes 1/4. You're right.
then it's also another way to play it because
Yep.
it's using every part individually.
Absolutely, yeah. But you'd get the same results. Now, there's going to be times where you calculate two probabilities together. The probability of A and B. When you combine probabilities, you multiply them. Okay, you don't add them, you multiply them. Okay? So let's sort of combine this. So let's say I had one dice in my hand. So I got a dice in my hand. One of these deals. Okay, I got a dice, and I got a deck of cards. Okay, so I got a deck of cards and some dice. What's the probability of me rolling a 3 and, at the same time, the probability of me drawing a heart? Okay, so here's the way it's going to go. For this experiment, I'm going to roll the dice and pull out a random card. What's the probability that I'm going to get a 3 and a heart by doing this? Well, we start with the first one. What's the probability of getting a 3? 1/6, right. What's the probability of getting a heart? 13/52. To combine the probabilities, I multiply them. 1/6 times 13/52. No, I'm not going to do the math on that. I know what the numerator is going to be, 13. Well, let's do it. 6 times 2 is 12. Okay. 6 times 5 is 30, plus 1 is 31. Okay. So it's 13/312. Does anyone have a calculator? Can someone please actually divide that? 13 divided by 312. It's going to be 0.0.
0.04166.
Okay, slow down. 0.041. Just give me the next number. 416. Okay. What's that as a percentage?
0.04.
No. Multiply it by 100. Times 100, right. It's 4.16%. So that's the probability of me getting that to do that. The probability of me rolling a 3 and drawing a heart is 4%. I got a 4% chance of doing that. That's how probabilities are calculated using the probability formula. Okay? So if we put this in sort of a graph, it kind of makes it stand out a little bit more. If you get a probability of somewhere between 50% and 100%, that's a good high chance of it occurring. If it's below 50%, it's a lower probability. If you go down to like 0 or less than 0, it's going to be like an impossibility. And if it's at 100%, it's certain. So in the last example, how would you describe the chances of getting a 3 and a heart?
I would say an impossibility.
It's not impossible, is it? But it's very low. Very low probability. Okay? Whereas when I said what's the chance of flipping a head, it's sort of an even, right? It's even chance. Okay. So dealing with probabilities is something that, again, you're going to deal with depending on the math course you take next year. In courses like pre-cal, it becomes more theoretical. In courses like the eventual consumer math course, it becomes more experimental with the way they deal with probabilities. Okay? So here's an example. What's the probability that 3 people, given the choice, choose a number between 1, 2, or 3, what's the chance that all 3 people would choose the same number? Well, one, I could just draw a tree diagram like this. Go, well, here's the 3 people. Chances that they're going to choose the 1s, the 2s, or the 3s. Okay? Then go, oh, there. All 3 people chose it. All 3 people chose 2, or all 3 people chose a 3. Okay? There are 27 different possible outcomes to this, where the people would choose different numbers. Out of those 27, there are only 3 where they chose the same number. Okay? Which is 3 out of 27, or 1 out of 9, or 0.11, or 11%. So there's an 11% chance that 3 people would all choose the same number. Right? And we could do an experiment with that. Okay, so I'm going to take you 3 right here. Choose a number between 1 and 3. Don't do, okay, between 1 and 3. Don't say it out loud, just put it in your head. Okay, ready? Number between 1 and 3. Now, there's an 11% chance that they're all going to choose the same number. What'd you choose? Okay. Now, what's the other thing that we learned about in the previous statistics that sometimes happens?
Everything is.
It starts with a B.
Oh.
Bias, yeah.
Bias.
There could be a bias there. It's possible that these 3, maybe in hearing his number, she, without her knowing, actually changed her number to 2. She had originally maybe picked 1, but she forgot 1, and when she heard Trey say it, she then went with 2. Maybe I should have had them write it down and hand it to me. That might have been a better way to reduce the bias. Maybe they came into agreement before they came in here today that they were going to mess with walks and they were intentionally going to screw up in any kind of experiment. Who knows? But that's an example of maybe a bias creeping in there. Yes?
Do that again.
Do it again? 3 different people? Yeah. Okay. So Garrett, you, and Brian, pick a number between 1 and 3.
Write it down.
Okay. Close your eyes and hold up how many fingers? Close your eyes and hold up your fingers.
Can I just say 1.4?
No. 3, 2, 1. So there we have all 3 different numbers this time. Okay. Now that would be an experimental probability. We could keep performing the experiment a number of times and see what the results are. Okay. Okay. So that's another way you could do the probability there. You could calculate it using best case scenarios using the formula, which is exactly what we just did, and come up with the 11% again. Okay? Or we could do what we just did. We could simulate the experiment. We could actually do this. We could also simulate it in other ways. We could roll dice and use the dice to represent people choosing numbers. Okay? There are lots of different ways you can simulate an experiment to get probabilities. Okay? Or we could do the actual experiment, which is what we also did. We actually asked 3 people to pick a number between 1 and 3. We could record their choices, write down the results, and come up with calculations. Okay? So probabilities are stuff that definitely can be expanded on. You could create entire big projects from probabilities. In the past, when I've taught this course, I've actually had, when the units were different, we actually did that. We actually made big projects based on probabilities. Not the case. We're not doing that this year. Okay. Last thing to look at is this idea of independent events. Okay? Shh. In determining the probability of something, it's important to realize that some events are connected with other events. Okay? When we toss 2 coins, they don't really affect each other. They might hit each other in the air. But the reality is it's still random whether they fall heads or tails. One coin does not affect the other. Okay? So it's said that these are independent events. If they're independent, then like I said, when we combine them, we use multiplication to combine them. If they are dependent events, as you probably learn in science classes, that doesn't work that way then. Okay? That's not dealing with probabilities of dependent events. Okay? Because those things are connected with one another. Okay? So here's an example. A coin and a die are thrown at the same time. What's the probability of getting a head and a 6? This is very similar to the one we just did. 1 over 2, 1 over 6. Combine those together using multiplication. 1 over 2 times 1 over 6 gives us 1 over 12. Okay? So the probability goes down with the 2 events in this case. Okay? So it gives us an 8.3% chance that we're going to get heads and a 6. Okay, here's the kind of questions you can expect on the assignment today. What's the probability of flipping a coin 4 times and getting 4 heads in a row? Well, the probability of getting heads, and then heads, and then heads, and then heads. Those are all independent of one another. So the first one is 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2, which is 1 over 16, which comes out to 6.25%. Okay? So basically, that's the way it works. Okay? You can use these examples to kind of calculate these values as you work through the assignment. Let's one more. You guys ever seen those spinners before in old sort of board games? What's the probability of getting a 4 or an 8? with that spinner?
1 out of 4.
No, read it carefully. 2 out of 8.
Or 1 out of 4.
Okay, or 1 out of 4. Okay, but let's be clear. The way it was calculated is the total number of outcomes is 8. The number of favorable outcomes is 2. There are 2 possible numbers. I can get a 4 or an 8. Those are 2, which is 2 out of 8, which can be reduced to 1 out of 4. Okay? Which comes out to 12.5%, which is low. Okay. Okay, so let's say we had a bag, and in it we had a bunch of marbles. Okay, in the bag was 4 blue marbles and 3 green marbles. 4 blue, 3 green. What's the probability of you drawing out 2 blue ones? Okay, here's where it gets a little harder for those of you who are actually doing this. Okay? When you draw the first marble, what's the probability of drawing blue? Well, first of all, how many total marbles? 7. How many favorable ones? How many blue ones? 4. So you got a 4 out of 7 shot at getting a blue marble. But then when you draw the second blue marble, how many marbles are in the bag now? 6. So the probability formula changes on the second marble. Okay? So the first one is 4 out of 7. But the second one is 3 out of 6. When you combine those two together, multiply them, you get 2 over 7. So unless it's said in here and then you put it back in, which it didn't, that changes the form. Those are the kind of tricky questions I've seen before in probability. Okay, I'm not going to reread this. These are your notes for today from this section. This is where it comes from in the curriculum, and I'll pass out the assignment for you guys to get started.